Hey, everyone. Thanks for coming. I'm Max. As was said, I'm from San Francisco, a place that's almost as beautiful as Iceland on a nice day. This is a picture of one of my favorite places there. Today, we're going to be talking about Bluetooth. Harald Bluetooth was a king of Denmark and Norway in the 10th century AD. He's widely known as the inventor of Bluetooth technology, but there are no Bluetooth devices in his day, so the technology went unused for hundreds of years. Actually, not quite. We're going to be talking about Bluetooth Low Energy, which is a variant of Bluetooth 4.0. And it's also called Bluetooth Smart. It was originally developed by Nokia in the early 2000s for lower power, lower bandwidth devices, like sensors and what we now call the Internet of Things. Bluetooth Low Energy can be thought of as a hierarchy of key value pairs, what we call as the generic attribute profile, and short for GATT. So let's take a look at what this looks like. So for example, let's say we have a heart rate wristband. In GATT terminology, we would call that a GATT server because it's what we connect to. A GATT server contains a collection of services. For instance, this server has device information, such as the vendor serial number and version, live heart rate data, and a battery service, which we can get up-to-date battery info from. Each of these services has a unique identifier, which we can use to request it from the device. A service contains a collection of characteristics. For instance, the heart rate service has live heart rate measurement data and body sensor location. In this case, the body sensor location would be the wrist, because this is a wristband. Services are really important for Bluetooth discovery. When you want to find a device to connect to, you do that by looking for a specific service. A service provides interoperability between different devices by different manufacturers because it's like a schema. If you have a heart rate service, it'll be the same no matter what device you're talking to. So for instance, a client like a phone can look for a heart rate service. And if there's a device that is offering the heart rate service out there, it will be broadcasting it. It'll be advertising, hey, I've got heart rate service. And then the client can start a connection with them. Web Bluetooth is a relatively new development. It's available right now as flagged in Google Chrome. So if you have Google Chrome stable, you probably already have a browser which supports Web Bluetooth. But it's still very experimental. It's still changing, and there may be unpredictability or even the potential for undiscovered security issues. So it's still, hold on to your horses. And it is also under development in the Servo browser engine. So now let's take a look and make our first connection to a Bluetooth device. This is called a myo. I'm wearing one right here. The myo is a ring of electrical contacts, and it is able to detect electrical changes on your skin and recognize like crude arm gestures. Like if I make a fist, it can recognize that. And let's step through in the console how to connect to this myo. And we're going to do this live. The myo, this is what the myo looks like in terms of services and characteristics. There's a command characteristic, which we can write values to send commands to the device. And there's a gesture characteristic, which we can use to observe live gestures from. Here's the IDs for those services. And as I advance these slides, these commands are going to be running live in the console, doing it live. So the first thing we need to do is we need to find or discover the myo device. The myo device is broadcasting, hey, I've got the myo control service. So what we're going to do is call navigator.bluetooth.requestDevice. And what we do is we pass it a filters object. And the filters is basically describing what the device looks like that we want to connect to. We also need to specify the gesture service here because we're going to need to access it later. We need to specify up front all of the services we're going to access on the device. So when we run this code, you'll see there's now a pop-up here that is offering to connect to the myo on my arm. This navigator.bluetooth.requestDevice requires user interaction. So you need to have it connected to a mouse click or a key press. We'll talk a little bit more about that later. When I press the connect button, the promise that is returned by request device will resolve. And as you see, we've successfully got just a representation of a Bluetooth device here. But we haven't connected to it yet. To do that, we call GATT.connect on it. Let's give that a shot. And let's wait. Cool. OK, so now we're actually connected to the device. Let's take another look at what the services and characteristics look like. As a demo, I'd like to show how to read and observe gestures from the device. So what we need to do is drill down into the GATT hierarchy and get the gesture service and then the gesture characteristic from that. To get the service, we call getPrimaryService with the ID of the service that we want. That returns a getService object. And then we want to drill down and get the characteristic. We call getCharacteristic on the service with the ID of the characteristic we're interested in. Characteristics are the values of the key value pairs in the hierarchy. Now that we have a reference to this characteristic, we need to do two things. We need to ask the device to notify us as the characteristic value changes, and then we can set up an event listener that will print out the gestures as they are received from the device. I'm calling a function here called parseMyoGesture because the data you get from these characteristics is an encoded binary. You have to decode it and interpret it into a higher level JavaScript form that's nice for us to work with. So when I press the next button and advance the slide, hopefully we should receive gestures from the device. I'm going to make a fist with my hand. Uh-oh. Oh, no, that's OK. There's one more thing that we have to do. We need to send a command to the Myo telling it, please start recognizing gestures and sending them to me. This is something specific to the Myo. We're turning on its internal classifier. But this is a great example of how to write a value to a characteristic. To do that, we're going to need to encode a binary characteristic, a command value. We do this using typed arrays. As you can see, this is a 5-byte array. Notably, the last byte of the array is the value 1. And for the Myo, that means please turn on the gesture classifier. And that's what it looks like on the console. Finally, we're going to write this command, please turn on the recognizer, to the control service of the Myo. This is similar to before, but we're just using a lot of promise chaining. The entire Web Bluetooth API is a lot of promises because each of these steps could involve asynchrony. So we're getting the service for the control service, then we're drilling down into the characteristic for sending commands, and finally we're writing a value to the command characteristic, which is the gestures command we have up here. And now we have live Bluetooth data from the Myo. So the Myo can recognize a couple things. If I spread my fingers, I can also make a fist. I can wave in. I can wave out. And I can tap my fingers. Maybe. Magic. This is so freaking cool. Oh my gosh. Like the first time I got this working was amazing because I've had this Myo device for about like 1 or 2 years, and I've never been able to use it on Linux because the manufacturer never made a device driver for Linux. But here in just like, 15 lines of code, we have a connection to the device, and we're able to get gestures off it. This is magical. Let's talk more about what's going on here. So from the Myo, which is like many of the Bluetooth devices I'll show you today, we're essentially getting a real-time stream of data, updates, from the device. If you're familiar with any functional reactive programming, perhaps you've come across this concept of a stream before. But you may be thinking of something that looks more like this. Or maybe this. But that's OK. Here's an introduction of how to work with streams in a reactive mindset. We're going to use a library called Xstream for this. Here's how to create a stream that will immediately emit 5 events, the numbers 1 through 5, as JavaScript objects. There we go. But the stream is not going to do anything until we add our first listener to it. A stream can be basically thought of as a value changing over time or a periodic sequence of events. The stream listener is basically 3 callbacks. A callback that is called when a new value is emitted from the stream, a fatal error callback, and a callback when the stream is complete and will no longer emit any values. So what we have here is a utility function that will print out on the console when each of these callbacks is called. So if we try that on our numbers stream, as expected, we get the numbers 1 through 5, and then the stream completes. But where streams get really powerful, gotta key into this Myo gesture here, is when you can use them to manipulate data and create data flows, processes by which we're transforming the data. So for example, we can create a new stream of the values multiplied by 10 based on our original stream by mapping a function over it. So in here, we're mapping multiply by 10 to our stream, and we're printing it out. Maybe I should switch back to the keyboard. As you can see, now we have printed out the numbers 10 through 50, and the stream completes. But where this gets really interesting is asynchrony. This time, let's try printing out the numbers 1 through 5, but let's wait a second in between each increment. Access.periodic will give us a stream that waits a certain amount of time and will count up into infinity. But we don't want to count into infinity. We want to count up to the number 5. So we can create another stream called finished that filters out any values that are not greater than 5. So the first value it will emit is when the count reaches 6. And then we can end our original stream, the count stream, when 6 is emitted. So then we can just get the numbers 1 through 5, waiting a second in between emits, and then the stream completes. Cool. Wouldn't it be cool if we could treat Bluetooth devices like streams? I've been tinkering with a library for doing this. The first thing we give this library is a description of the device we'd like to connect to. This looks like the call to navigator.bluetooth.request device. We're passing in filters and optional services. But now we give it a listen object. That's a description of the services and characteristics in those services that we want to observe as a stream. And what this library does is it gets that characteristic, it starts notifications running from them, and it hooks up an event listener, and it emits those events as a stream. And if the device disconnects, it will reconnect automatically. So here is a view of the live data coming off of the Myo device on my arm. We're printing it out in hex format. And if I make a fist, you can see the value changes from 0 to 1. And we're using this library we're just pulling out the gesture service and gesture characteristic as a stream. But that's not very nice to look at or code with. So to parse this Myo gesture, here's an example of how you can decode one of these binary events. We have a mapping from values to string gestures. And we're just going to get the value of the gesture in binary from the Myo, look it up on our table, and return the value if we have a match. And that's what this looks like. So now we have a live stream of high-level, easy to work with gesture data. You'll notice there's kind of a funny $ after raw gesture. That's a convention for indicating. Whoops. Have to get a little bit less excited with my arms. That's a convention. The $ tells us that the variable we are working with is a stream. And as we'll see in the slides to follow, all of these slides are transforming one stream of data into another stream of data and processing it as we go. Let's look at a second device. This is a Bluetooth heart rate monitor. The way it works is it shines a green light into your wrist, and it detects the minute changes in color from blood pumping into and out of your skin, out of your veins, underneath your skin. This device is similar to the Myo. We're looking for a device this time that is advertising the heart rate service, and we're going to dig into it and get the heart rate measurement characteristic from there. You'll notice that instead of a variable where I'm holding an ID for these services and characteristics, we're just passing plain old JavaScript strings in here. The reason is the heart rate service and heart rate characteristic are standard services provided by the Bluetooth SIG. Back to that in a moment. Here's the binary data coming off of the heart rate stream, coming straight from my arm right now. So you may be wondering where you find information about these binary representations and what kind of services and characteristics there are. This is a website from the Bluetooth SIG where they describe each of these characteristics and the data formats inside. So we can drill down the characteristics listing to find heart rate measurement. And then when we go look into there, we find a table describing what each byte does and how to interpret it, what the description is, what the units are, et cetera. And this is what the heart rate measurement one looks like. And then you can turn that into a big old JavaScript function. We're not going to go into the details here, but what's interesting about this function is it's actually straight from the Web Bluetooth spec draft. It's used as an example there. So if we apply this parse heart rate function to our stream of binary data, we can get a live feed of heart rate data as a stream. You can see here that there's the the heart rate value. That's in beats per minute. And there's also RR intervals, which is the amount of time in between each heart rate pulse. Now we're going to look at the last and most exciting device for me, which is a bicycle sensor. This bicycle sensor sits on the chainstay of your bike. We have one right here. And it basically, there's two magnets on this bike. There's a magnet on the crank here by the pedal, and there's a magnet on the spoke of the bike. And as these magnets pass by the bike sensor, it's going to count how many times they've passed by. Frankly, it's a glorified stopwatch. But a stopwatch isn't a very useful piece of data to work with. To connect to the cycle sensor, we're going to use the cycling speed and cadence service, which this device advertises. And as you can see, these are also friendly string names. So this is a standard service that you can refer to by its name alias when you're using the Web Bluetooth API. So let's look at the binary data coming off of the device. If I give the wheel a turn, we should see it update in a moment. Cool. So what it's doing, we can try turning the crank as well. Really exciting. All right, it'll get more exciting in a moment. I'm going to save us the trouble of writing a parser for this and jump straight to the abstract data we're getting off of the device. As you can see, if I give the wheel another turn, you're going to see indeed that the revolutions of the wheel are ticking up. And when I turn the crank revolutions tick up as well. And we also have timestamps for those values, which we can use to calculate the speed of rotation. But first, let's calculate distance. Distance is really easy. We take the circumference of the wheel and multiply it by how many times it's turned around. And then we can get a stream of the distance traveled. We'll use this in our bike computer if we're going to display it to the rider. And this is in kilometers. Cool. Now let's figure out how to create a stream of the speed of the bike, because that's what we're really interested in, going fast. We want to measure the speed, first of all, in revolutions per minute, the number of times the bicycle wheel goes around. To do that, we're going to take two samples. We're going to look at, over time, how many times the wheel is rotated over how much time. But we haven't looked at history yet in the context of a stream. How do we get that previous value? Because currently, the streams I've shown you so far are just the current most live value emitted every time. Well, Xstream has us covered here with an operator called pairwise. And this operator, you basically apply it to your stream, and it transforms your stream into a new form that emits different types of values. What pairwise does is it will emit consecutive values as array pairs of a stream. So if we call print stream on this, you can see 1 to 2, 2 to 3, 3 to 4, et cetera. So we can use this to pair up our samples of data from the bicycle computer, and we can use that to calculate RPM. First, we're going to do cadence. Cyclists like to know how quickly they're turning the pedals, and we measure that as cadence directly as RPM. So this is how quickly I'm turning the pedals right now. Yeah. But for the speed of the wheel, what you see happening here is we're taking the pairs of samples, and we're just doing a little bit of object munging before we pass it into a utility that does the math for us. We're pulling out the crank revolutions from the first sample, and then the crank revolutions from the second sample. And then the function revs to RPM is going to just do the math, comparing how much time has passed and how many cranks have happened. We can do that for speed as well. So if I turn the wheel, we can get RPM off of the wheel. And finally, what we want to do is convert that RPM to kilometers per hour. And we do that by multiplying it by the circumference of the wheel, giving us how much distance we are traveling over time. Let's give this another whirl. Whoops. Yeah, so there you have it. we've created 4 streams of data now coming off of this bike, well, and my arm. This is all completely live. You can see my heart rate is going at a nice 120 beats per minute. Everyone's favorite electronic music tempo. And as we interact with the bike, we can get live data off of it. If we take a eagle's eye view of what's going on here, we've connected to a heart rate sensor here. We've converted a stream of binary data into abstract heart rate data. Similarly, we've connected to the bicycle sensor, and we've got a system of streams that are all, one step in the data processing flow. Whoops. Yeah. So based on the parsed revolution counts and timestamps, we can derive the distance traveled, the wheel RPM, the crank RPM. And from the wheel RPM, we can do a little math and get the kilometers per hour. And now we have 4 streams of bicycle information. There's one last step to make an awesome bicycle computer, which is we need to pipe this all into the DOM somehow. We can use handlebars.js for this. Get it? Just kidding. Instead, we're going to use cycle.js for this. There's no relation between cycle.js and Bicycle.js, by the way, which is the name of this talk. Cycle.js is a really cool library for building applications and behavior systems out of streams. In Cycle.js, your view is also a stream. So we take our stream of all these 4 different cycling metrics that we've collected up, and we transform that stream into virtual DOM. And when our stream emits virtual DOM, in this case the component Bicycle.js, each emitted virtual DOM gets diffed with the current state of the page, and the page gets updated. And in the end, we get something that looks like this. And I'd like to give it a spin. Now, it's very important to wear a helmet. Oh, sorry. It's very important to wear a helmet when you ride a bicycle. Someone once told me that your head is about the toughness of a ripe watermelon. So keep that in mind and be safe. It's also really important to wear shades when you're bicycling because it looks cool. And oh, wow. I probably should have toned down the gestures. But it's cool. We've got wireless control because it's Bluetooth, so everything's fine. Let's give this a spin. This is my everyday ride, you guys. Just riding along in Harpa. Really cool. So now you have it. Somehow we managed to go into negative distance, but, time travel. And we've got some cool graphs. Everything works great. So that's Bicycle.js. Thank you. Now, as you saw by my rudely advancing the slide too early, the point I'm trying to make about all of this is that the web is changing. Rather, our expectations for the web are expanding. Bicycle.js is an example of a web app that can run pretty much like a native app on your phone. It works offline thanks to a service worker, and it connects natively to your Bluetooth devices. This is previously something that was a task relegated to native iOS and Android devices. In fact, for any of these gadgets, many of which you may own, the first thing you do when you're setting up one of these gadgets is you download and install an iOS or an Android app. And if you're a PC user, you're just left in the dust because it's not supported. But now, that's the whole point of the web. The web works everywhere for everyone. So the promise of Web Bluetooth is now these interactions with real physical devices can happen straight from a web page. That's really powerful. Another really cool thing, if you see any node bots happening around, if you have a node bot with a Bluetooth low energy chip, you can actually send commands to your node bot now straight from the browser. This is amazing for education and for creative experimentation. The barrier to entry of talking to these devices has just been decimated. Now you may be wondering a little bit, and we're going to use this to conclude, what are the security implications of this amazing wireless communication with devices around us? And I'm going to talk about this a little bit. Remember how I said in the beginning that it requires user interaction before you can connect to a device? That is really important because many of the devices out there may not have been designed with an adversarial attacker in mind. They're like, oh, it's cool. It's just cell phones or whatever. You just have to install an app. But now, what, a web page can talk to my Bluetooth device? Even worse, these potentially insecure or buggy devices probably will never get their firmware updated. So there was a serious concern about being able to send like nasty packets to Bluetooth devices. But there's two defenses against this. First, the Web Bluetooth API is very high level, so the potential for crafting nasty packets is limited. But also, every interaction with a Bluetooth device has to start with an interaction with the user. And you can play little phishing games, but it's very hard to spoof getting that, like, do you want to connect to a device dialogue? Now, there's a couple little nitty-gritty things that are interesting, which is that Bluetooth devices around you can be a fingerprinting method. Like if you have a smartwatch or a smart TV around you, and you open up your browser and it's just able to scan willy-nilly for devices, that may be used to fingerprint you. But thankfully, that's also gated behind a user interaction. Finally, and this is just nice to know about, whenever you're dealing with Bluetooth or radio, there's a potential of leaking your existence to the outside world. So I don't know, unless you're in a spy movie, but if you open up your phone and scan for Bluetooth devices, you're making your phone discoverable. And what that means is it's broadcasting, hey, I'm here, I'm a phone, cool. Or what, I'm a phone, I'm talking, I'm alive? Anyway, your laptop is going to do that too when you open up a web Bluetooth scan. That's worth knowing about. If you want to learn more about Web Bluetooth, I suggest starting here. The Web Bluetooth standard drafting process is very open, and they have this great document if you go to their GitHub with a browser support matrix for Web Bluetooth. And there's also some really cool demos and like sample algorithms offered by the Chrome team. I want to say thank you to Andre Staltz for creating cycle.js and Xstream. That was majorly inspiring and influential for this talk. This entire presentation has been a cycle.js application. It's composed using these streams of values and behaviors. And I also want to thank Haldor, who is sitting somewhere over here, for loaning us his totally sweet bike. This wouldn't have been possible without it, so thank you so much.